Hello everyone. Welcome to the sixth lecture of the fifth module, which is on combinational circuit design. So in the last lecture, we were discussing about the pass transistor logic, and we looked at the advantages that we can realize any logic with minimal number of MOSFETs. That not only leads to a reduction in the area, but it also reduces the delay. However, we saw that there are three major problems with this kind of logic. First, the output or the nominal logic level high is only VDD minus VTN. Second, you cannot cascade them in such a way that the output of one level of pass transistor becomes the input of the gate of the other level of pass transistor. And third, it's non-regenerative, right? So now let us look at some of the technological innovations or some of the innovations which have helped to mitigate these issues faced by the pass transistor. So the disclaimers remain the same. So the first issue at hand is, how do we restore the logic 1? That is, instead of having or realizing VDD minus VT of n, how do we realize a perfect VDD as logic 1 for pass transistor based logic? So there are basically three levels of innovations, I would say. One is at the circuit level that we'll be discussing right now. So let us look at it. So that circuit is known as level restorer solution, or I would say this is, you apply a feedback and then you use a level restorer MOSFET. That's actually a P MOSFET. And then you are able to, pull the node from VDD minus VTN way to VDD. So let us look at that circuit. Let us look at this level restorer circuit. So a level restorer circuit looks like this. So we know for a fact that, if we only had this pass transistor based logic, then even if A is equals to 1 and B is equals to 1, our node Vx will be charged only till VDD minus VTN. And what is that VTN? VTN is a function of body bias as well. And why Vx? Because Vx is actually the source voltage of this MOSFET, right? And MOSFET. So if Vx is increasing, then the body to source junction is reverse biased. And we know for a fact that when body to source junction is reverse biased, our threshold voltage increases. Therefore, this VDD minus VTN becomes even smaller, right? However, if we have an inverter connected to this output, like node X, and then if we are taking up feedback from here, what happens exactly is, even if A is equals to 1 and B is equals to 1, the voltage at this node is VDD minus VT of n, and that is higher than the inverter switching threshold of this inverter. So even if it is symmetric inverter and its switching threshold is VDD by 2, so this VDD minus VTN of Vx is always greater than VDD by 2. And when your Vx here is greater than Vm, what happens? The output goes low. So the moment the output goes low, you see that the output is connected to the gate electrode of this P MOSFET. So if the gate electrode voltage is low, effectively VSG is positive, more than mod of VTP. And as such, this transistor turns on, this level restorer MOSFET turns on, and it starts to pull this node X towards VDD, or it also charges this node X towards VDD. So instead of VDD minus VTN of Vx, we get full VDD or we get full swing, right? So the moment this MR is activated, this Vx is pulled to VDD, and as such, full swing is restored. Now the nominal logic level 1 is VDD itself. However, as I told, there's no free lunch or VLSI. There has to be a trade-off. So what is the trade-off here? So before discussing about that trade-off, let us talk about the static current path. So here, if you look at the circuit, there's no static current path between VDD and ground. I mean, VDD and ground are not connected ever through a MOSFET which is not in the cutoff mode, right? So that way, even static leakage current or static leakage paths are minimized. So static power dissipation is minimized. I won't say it's zero, because there would be subthreshold leakage current and static power dissipation would be finite and significant. But as compared to the previous circuits, like when you had pure resistors as load, here the static power dissipation is reduced. Or even in the pseudo NMOS case, pseudo NMOS logic, as compared to those cases, there is no static path over here for currents to flow between VDD and ground, and as such, static power dissipation is minimal. Also, now let us talk about the trade-off. So what is the trade-off? So if A is equals to 1, B is equals to 1, we saw that the circuit is able to pull this node Vx to VDD. But another thing is also important. I mean, the reverse of this should also be true. That is, when A is equals to 0 and B is equals to 1, this should be pulled down to the ground as well, right? However, now let us look at the case when this node X is transitioning from logic level high to logic level low. Let us say that B is equals to 1 and A is equals to 0. So in that case, what happens? I mean, when we had A is equals to 1 and B is equals to 1, then this node was charged to VDD because of this level restorer. Now what we are doing is we are immediately making A is equals to 0. So when we are making A is equals to 0, this effect of, only when the node X gets discharged below this VM, this output will go high and this level restorer will be turned off. But before that, as this is at VDD and it is gradually discharging through this, gradually discharging to ground via this MN, what happens? This MR starts, like this MR tries to charge this VX to VDD and this MN tries to discharge it to ground, right? So there is a tug of war. So there's a tug of war going between MR and MN. Only when this node Vx is pulled down below Vm of this inverter can this node be 1, and then this level restorer will be turned off. But before that, what is happening? This MR tries to charge this to VDD, MN tries to discharge it to ground. So if the pulling strength of MR is larger as compared to MN, this node will never go to, this node will never go below Vm of this inverter, and this X will never go to 0. So the sizing constraint that we have now is this size of Mn should be such that its current driving capability or its pulling strength should be higher as compared to Mr. Why? Only if the pulling strength of Mn is higher as compared to Mr, the voltage of this node Vx will be pulled more towards the ground, or it will be pulled below the below the Vm of this inverter, and this output will turn 1 and turn off this Mr. So that is pretty important, right? So now sizing constraint is that, we have to size these Mr and Mn such that Vx is less than Vm, such that Vx is less than Vm when A is equals to 0. It should be Mn actually. So it no longer remains a non-ratioed logic, it becomes a ratioed logic now, right? Earlier it was non-ratioed logic, right? The pass transistor, we sized it as 1 and that was sufficient. But now it becomes a ratioed logic because now we have to relatively size Mr and Mn such that, the Vx is less than or equal to Vm when A is equals to 0. So that is the sizing constraint over here. Also, when you are introducing these inverters and this level restorer MOSFET, then what you're doing essentially is you are increasing the internal capacitance at this node X. And because of that, you're also increasing the delay of this circuit. Also, the rise time at the output node increases. So here by output, I want to say this output. Why so? Why is the rise time of the output increasing? Because when would output rise? When X is falling. So what is kind of, impeding, or what is kind of impeding the falling or transition of node X from 1 to 0? It's basically this level restorer. As long as this level restorer is turned on, it will, restrict, or it will kind of oppose the dropping of this voltage at Vx towards ground, right? So it will try to pull it up to VDD, and as such, it will oppose the transitioning of Vx from high to low. And if Vx is going from high to low, the output is rising, right? So the rise time actually increases because Mr is trying to pull this node X towards VDD before turning off. However, at the same time, it would also facilitate in reducing the fall time. Why? Because the moment this node X gets charged to Vm or VDD by 2, this node actually switches to 0 and this level restorer turns on and it quickly charges this to VDD. Therefore, the output fall time, which is actually related to the input rise time, that actually reduces significantly. Because this level restorer, as soon as this Vx is charged above Vm, this goes down and level restorer is turned on and it charges this quickly to VDD. And as such, the fall time of the output here, this out node, it actually reduces, and rise time of this increase, or rise time of this reduces and the fall time at this reduces. So introduction of this leads to an increase in the rise time, but leads to a reduction in the fall time. It restores the full swing that we have seen, right? Because here, if you size Mn and Mr properly, then logic level low is ground and logic level high is VDD. And also, this node X over here is no longer at high impedance, right? We saw that, this node X was at high impedance when we used only one pass transistor and not the second one. So here, this node X is never at high impedance. It's always connected to either ground or VDD via these low resistance paths, right? However, since the capacitance have increased and you have introduced a large number of transistors, it will increase the area as well as the power dissipation. Now let us talk about the second level of innovation which people have introduced, which is in the technology. So what people introduced is, in terms of technology, what we can do is, can we design a transistor which has got zero threshold voltage? So if we have zero threshold voltage, effectively VDD minus VTN will be VDD. So there won't be any drop in the logic level 1. So that is one of the innovations that people came up with in the technology. So other than pass transistors, so what they proposed was, let us use a transistor which is having a zero threshold voltage for the pass transistor, and other than that, for all the other circuits, let us use nominal transistors which are having a high threshold voltage. I call it HVT, high threshold voltage, or HVT. VT is your threshold voltage. So other than the pass transistor which is having a zero threshold voltage, let us use high threshold voltage transistor for all other devices. Now let us go back to the problem of changing threshold voltages. How can we change the threshold voltage? What are the parameters on which threshold voltage depends? So threshold voltage basically by design depends upon channel doping and the oxide thickness. See, changing the oxide thickness of different MOSFETs on a chip is actually process-wise more complex. Doping is actually somewhat easy to change. So people in general change the channel doping itself and not the oxide thickness. I mean, they also change oxide thickness when you have to sustain a higher voltage. For instance, when you make a power MOSFET that has to sustain more than 10 volts, then you use a thicker oxide. You cannot work with thin oxides because they can break down. But in general, if you have to realize different threshold voltages only, then you can change them by changing the channel doping. And this is what typically the foundries do nowadays. So in all the foundries, I mean, whatever PDK you work with, or whatever technology you work with, whatever foundry you are sending your design for tape out or for fabrication, they'll give you 2 options or 3 options always. So you'll always get this high VT. High VT, it is also available in low power or low leakage form. I mean, so high threshold voltage means a lower subthreshold current. So that transforms into a low power or a lower leakage current. If it is a low VT transistor, then subthreshold current is large, but VGS minus VT, which dictates the on current, that is large. So it's called high performance. Your effective current that you can drive through this low VT transistor is large, and as such, it gives you high performance or lesser delay. And also we have another flavor which is called high voltage, which I told that there the oxide thickness is large. These transistors, the high voltage transistors, are typically in some microns. However, this low VT and HVT, they can come even in the smallest size provided by the foundry. However, the point to be noted is, since we require now 2 types of MOSFETs in design, I mean, we require a HVT as well as a LVT, and LVT, the threshold voltage should be 0. Since we require 2 types of MOSFETs, therefore the process complexity is large, right? Although it's large, but nowadays, all the foundries provide it. So for in today's world, this doesn't make much of a difference because we already have HVT transistor or LVT transistors. So whenever you are working with, these MOSFETs in any industry, you will definitely find out that either they use HVT, LP or LL for the MOSFETs, which are consuming low power or low leakage, but their on current is also smaller. However, there would be another flavor where the on current would be large, but the subthreshold leakage current would also be large, or the leakage power dissipation would also be large. This is typically used in areas where delay is most important. And again, there would be some devices, or there would be some circuits where you need to sustain high voltages. For instance, the NAND flash or your flash memory in your mobile phones, the controller there, or the decoders, column decoders, and so on, they use high voltage transistor because these flash devices need a programming voltage in excess of 10 volts. So you see in your mobile phone itself, for accessing these flash drives, you have to generate a voltage more than 5 volts, which is your battery. So you use charge pump, and then you use high voltage transistors that can sustain those 10 volts of, that can sustain that 10 volts without degrading or without, breaking down. So all these 3 flavors are available nowadays in all the foundries. So whenever you're designing circuits, you check out this PDK, you'll definitely find these 3 flavors of MOSFETs. So with this, let me go ahead and tell you that even if somehow you make this VTH 0 by appropriate channel doping, still what would happen is the body effect would still be there and it would still deteriorate the logic level, right? Also, when you're talking about LVT transistors with zero threshold voltage, so there would be high subthreshold leakage current, right? Because the subthreshold leakage is exponentially, like it goes or increases exponential as a function of VGS minus VT. If VT is zero, therefore subthreshold leakage current is high. If VT is large, subthreshold current is smaller, right? So for LVT MOSFET, subthreshold leakage current is larger, and as such, static power dissipation would increase when you're using LVT transistors for fast transistor logic. However, such kind of design works fine if it is being switched continuously, because if it is being switched continuously, then it's a dynamic power dissipation which is more important. It is not in static condition for large number of time or large amount of time. So if you are making static circuits with this kind of design, it's not advisable to do so. But if you are making or using this kind of approach in designing a circuit where the input is changing continuously or the output is switching continuously, then it makes a lot of sense to go for this. Okay. However, there's another problem with this kind of circuit, that or this kind of LVT, using this kind of LVT transistor, that it can lead to unintentional leakage paths. For instance, let us say that we have these two, we had A here, we have A bar here. So A is 0, and then we are using an inverter to, let's say, feed it to this B. Let's say this B and B bar both are, LVT or zero threshold voltage transistor. Here I have shown it as a depletion mode transistor. Depletion mode is also a zero. It can also be made as a zero threshold voltage transistor. So let's say we have a situation like this. So if we have complement inputs here, then what happens? There is a path. I mean, since this threshold voltage is 0, it's always on, right? It's almost always on. So there's a path from VDD to the ground. So the current would actually flow like this, and it would not even charge this, internal capacitance here. So the output here, it would be at the same level always. So in static condition, it can lead to unintentional leakage paths such as this, and that is a disadvantage of this. So we never want these MOSFETs to be turned, on always, because if the threshold voltage is 0, any voltage, if B is even if B is 0 or 1, these would be on, right? Because threshold voltage is 0. So even if voltage at B is 0, it will be on. Okay, so these are the problems with this kind of, technology level solution. Now let us go for another solution, which is a design solution. So this is actually more promising, and it is known as transmission gate. So we know that, N MOSFETs pass a strong 0, while P MOSFETs pass a strong 1. So someone came up with this wonderful idea that why not, combine both of them together and use the best of both worlds, right? So why not combine them, put them in parallel, and then combine their driving efficiency to get the best of both worlds. When you want to pass a strong 1, it will be passed through PMOS. When you want to pass a strong 0, it will be passed through NMOS. So you just have to place them in parallel, right? And then the problem is, if you want only one of them to be active, then you have to get another control signal, which is C over here. So this control signal, you have to apply both the control signal and its complement at the gate of these two MOSFETs that you have placed in parallel. So this transmission gate can be simply viewed as a bidirectional switch, which is controlled by input signal at the gate or the control signal at these gate electrodes. Now, since you have used two MOSFETs, therefore the area has increased, and also the parasitic capacitance at these two nodes have doubled, right? Another point, since you have also introduced these new control signals, C and C bar, these also have to be routed throughout your circuitry. So complex routing, it introduces routing complexity, because now you have two more control signals which need to be routed throughout your chip. However, the advantage is that, rail to rail swing is already realized, because if input is 0, then NMOS will pass it perfectly. If input is 1, then this PMOS will pass it perfectly at B. So for mux-based design, I mean, this transmission gate is best for designs which are mux-based. So this multiplexer, which can be used to select one of the two inputs, is, that can also be used to realize any of the, logic gates. So the mux is actually very efficiently realized using transmission gate as compared to static CMOS logic. So whenever you have to do a mux-based circuit design, you always go for transmission gate. So how can we use mux to design different logic gates? So what exactly is mux? Let us see that. So a mux looks something like this. It has a control signal S. Depending upon whether S is 0 or 1, it passes the inputs at its output. So if S is equals to 0, it will pass I0. If S is equals to 1, it will pass I1. So what is the output over here? It's simply S bar times I0 plus S times I1. Now this S, I1 or I0, they can be either Boolean variables or they can be made 0 or 1. And once you do that, you can actually realize all sorts of logic gates with the help of these mux. So let us see some of the examples. So here you see that if this control signal is A, and if 0 and 1 are applied like this, so what is X? X is equals to A bar. When A is equals to 1, 0 is passed. When A is equals to 0, 1 is passed. So it's A bar. That is a NOT gate. Let us see this case. If A is the control signal and B is applied here, when A is equals to 0, 0 is passed. When A is equals to 1, A dot B is passed. So it's A dot B, right? Now, let us see this case. So here A is the control signal, B is applied here. So the output is, when is the output 1 here? So the output is 1 here whenever A is 1 or B is 1. So if A is 1, then output is 1 because 1 is passed. Now, if B is 1, then regardless of whether A is 0 or 1, 1 has to be passed to X, right? So it can also be used to realize OR gate. Since there are 3 variables here, S, I0 and I1, and all of them can take either a variable, either an input, or a 0 or 1. So there are 3 raised to power 3 combinations of inputs, like these 3 inputs. And with that, you can realize almost all the logic gates. So this mux-based design, whenever you have to go for this mux-based design, always remember, go for transmission gate-based realization. It will become very clear now. So let us look at the efficiency of the transmission gate that I was discussing about. So this is a 2:1 mux realized using a transmission gate, right? So if you look at here, you see that this 2:1 mux can be realized only using 6 MOSFETs. So 1, 2, 3, 4, 5, 6. So realizing 6 MOSFETs, you can realize a 2:1 mux, and then you can go ahead and design any gate with this mux just by using a suitable combination or appropriate combination of inputs. So this is realization of XOR gate, but let me just go ahead and tell you about this mux first. So 2:1 mux can be implemented using 6 MOSFETs only here. When you do it with static CMOS, it requires 8 MOSFETs. So there's a reduction in the size as well as area as well as number of MOSFETs, also in the parasitic capacitance, right? Also, the best part about this kind of logic realization using transmission gate is you can realize the XOR gate with only 1, 2, 3, 4 transistors plus 2 transistors when you have to realize both B bar and B. So here you see that we don't require A bar, we only require B and B bar. So using only 6 MOSFETs, you can realize a XOR gate here for this transmission gate based logic. However, when you talk about static CMOS, you require 8 gates, you require 8 MOSFETs first, and then on top of it, you require 2 inverters for generating both input and its complement, right? So here also, compared to static CMOS, it is quite advantageous. The number of MOSFETs used is just half. So you look at the efficiency of this transmission gate. And since XOR is I would say XOR is kind of an inherent component, or the adders or registers, they use XOR like hell. I mean, full adder, it's basically A XOR, B XOR, C input, like where C in is the carry. So such efficient XOR gate implementation using transmission gate helps you to design fast adders. So whenever you have to design adders, then you go for transmission gate design. So whenever you have to do mux-based circuit design, or whenever you have to use, or whenever you have to design adders, go for transmission gate based logic design. And here also the output is connected via low impedance to ground or VDD, right? So that is also an advantage. Now let us model this transmission gate. So transmission gate in general is modeled as a bidirectional switch, something like this, which is its symbolic representation. And if you make its electrical equivalent, is nothing but an equivalent resistance, and there are these 2 intrinsic capacitances at the input and the output that these 2 MOSFETs introduce. So now let us look at this Cx value. So if we are designing this such that, these two, like both NMOS and PMOS have same equivalent resistance, then NMOS should be sized as 1, PMOS should be sized as beta. So what is Cx here? Cx is simply 1 plus beta gamma Cg0, right? So Cx is 1 plus beta gamma Cg0. And what is R equivalent? R equivalent is nothing but, since these two MOSFETs are in parallel, it's basically the parallel combination of the resistances offered by these two MOSFETs, right? So R equivalent is simply Rn parallel Rp, and Cx is 1 plus beta gamma Cg0. Now let us find out the equivalent resistance, or let us look at the equivalent resistance of this transmission gate when we are passing a 1 from in to out. So that, there is this input. Here the input is going from 0 to 1. So let us look at how is the output changing, or what is the equivalent resistance. So as output is going from 0 to 1, because the input is going from 1, like input is going from 0 to 1, so output will go from 0 to 1. As it is going from 0 to 1, you see that equivalent resistance, that is Rn parallel Rp, it remains almost constant. However, resistance of the NMOS increases significantly, and the resistance of the PMOS decreases as one charges the output node towards VDD. Why is it so? Let us discuss that. So as your output voltage is changing, as your output voltage here is changing, depending upon the relation between VDS and VGS minus VT, these MOSFETs will traverse through different operating regimes, right? So let us take few cases and try to understand it. So let us take the case when Vout is smaller, right? So when Vout is smaller, what is its VDS? Input is 1. So VDS is high. And what is VGS minus VT? So VGS is also, so this node, the output node is the source node for NMOS. The input node is 1. So it is the drain node for NMOS. Okay. So input is 1, and now it is being passed to the output through this NMOSFET and PMOSFET combination. So if Vout is small, I mean, initially, when you are looking at Vout, when it is small, so your effective VDS of this NMOS is larger as compared to VGS minus VT, right? So in that case, your NMOS is in saturation. Similarly, for PMOS also, when Vout is small, it is in saturation. So when your NMOS and PMOS both are in saturation, so the resistances are like small. So let us talk about NMOS first. So its resistance is small when it is in saturation. Now what happens? If you will try to calculate its resistance, so it's simply VDD minus Vout by the current flowing through it, right? The voltage drop across this NMOS divided by the current that is flowing through the NMOS. So it's simply VDD minus Vout divided by the current. Here we'll use the saturation current expression, and here I'm using, the velocity saturated current expression. So once you do that, it comes out like this. However, what happens as your Vout goes towards VDD minus VTN, effective VGS becomes what? If this is 1, then it is VDD minus VTN, that is close to VT. So effective VGS becomes close to VT. And if the output node actually increases beyond this VDD minus VTN, then what happens? This NMOS gets into cutoff mode, right? Why? Because its source node is actually getting a voltage which is more than VDD minus VTN. How will that be charged to a voltage more than VDD minus VTN? Because of this PMOS. So this PMOS can charge it way to VDD. So what is the case is that, when Vout goes above VDD minus VTN, then the NMOSFET goes into the cutoff mode and its equivalent resistance becomes very large. So that is what is happening. The moment here Vout goes above VDD minus VTN, the resistance of this shoots up. However, even when Vout goes high, PMOS is still in the linear region. Why? So let us try to understand why this PMOS doesn't go into cutoff, why the NMOS is going into the cutoff. So this Vout, or this output node, is source of this NMOSFET, whereas this Vout is the drain of this PMOSFET. So when effectively your source voltage is changing, your VGS is changing for the NMOSFET, while your VGS is not changing for the PMOSFET. It's only VDS or VSD which is changing for the PMOSFET. So since the VSG is constant, it won't get into cutoff. However, depending upon the VSD, it will switch from saturation when Vout is low to linear regime when Vout is high. Now you remember from the plot like this, I mean, if you looked at the plot of ID versus VD, I mean, when you are plotting IDP, mod of IDP versus mod of VDS, of a P MOSFET, you saw that the curve looks something like this. So in your I versus V, the plot looks something like this. So here in the saturation regime, the resistance is high, and in the linear regime, the resistance is low. Why? Because the slope is smaller in the saturation mode, the slope is higher in the linear mode, right? So as to say, the current doesn't change much when your voltage is changing. So what does that represent? That represents that the resistance is high. If the current is changing largely when you're changing your voltage, that means that your resistance is smaller. So for a P MOSFET, what happens? When you change the V out, only your operating regime changes from saturation to linear, and as such, your drain current decreases, because in saturation you have a higher resistance, in your linear you have a lower resistance. And since R equivalent is parallel combination of both of them, it remains almost constant throughout the swing. And similarly, you can when you do this analysis, when A is equals to 0 and then we are passing this to this output, you'll find out that even then R equivalent is almost constant. So this makes it easy for us to model a transmission gate based logic design. So let us take the case when we have a chain of transmission gates. So this is something which is always encountered when you design adders and mux based design. So adders, whenever you realize XOR gate, or whenever you design adders, since XOR gate is easy to define using this, so we always use transmission gates. So let us see, we have a chain of these transmission gates. Ignore this C by 2, it should also be C. And let's say we are applying a step input at this, and then we are finding out the delay at this input Vn. So we'll use the Elmore delay approximation, and that gives out the delay as 0.69 C R equivalent n into n plus 1 by 2. That is, your delay is actually proportional to n square, where n is the number of stages, transmission gate stages. Now this is large. I mean, since Tp is varying as square of n, so this is kind of telling you that the delay increases significantly. And also, since this is non-regenerative, so first there's a large delay because of this dependence on n square, and second, rise time will also be large for long stages. Why? Because it's a non-regenerative circuit. So what we do essentially is, in order to reduce the delay and in order to restore a high rise time or fall time, we break this chain and then we insert buffers after every m stage. So let us say we have total n number of stages. So what we do is we break them into n by m number of stages and insert buffers. So each individual stage will have m stage, and then we add a buffer, and then again m number of transmission gates, then again a buffer, and so on. So such total entities would be n by m. So it looks something like this. So we have total n number of these stages. After every m stage, we introduce a buffer. For what? For regeneration of logic. So in that case, what happens to our delay? So delay is simply 0.69 n by m. That is the total number of these entities. And what is the delay of one such entity? Delay of one such entity is C R equivalent m into m plus 1 by 2, because m is the number of stages in one such entity. This is for n by m such entities. And then to that, we also have to add the delay of this buffer, right? And how many such buffers are there? N by m minus 1. Why minus 1? Because at the output, we don't have a buffer. So this is the delay of, an arrangement in which you have broken the chain and added buffers every m stages, so as to reduce the delay and to realize a good rise time as well. And you see that this expression is now proportional to n. So you see that the effective increase in the delay as a function of n is reduced from n squared to n. So it's better, right? Also, if you differentiate this, if you differentiate this function with respect to m and equate it to 0, what you get is the optimal value of m comes out as 1.7 root Tp buffer divided by C into R equivalent. So doing this calculation, you'll find out that m optimal is like for 0.25 micron technology, it's close to 4. So you can find out this value of m optimal as well. That is, after how many number of such stages we should insert a buffer.